Hello, everybody. Welcome back to a very cool lecture about a subject with a really weird name. So, this is about topology, at least topology of the real numbers. So, topology is a very, very interesting branch of mathematics all on its own. I'm not going to say very much about it other than just to tell you what it is so you don't wonder about what the title is. In some sense, the easiest way to tell you what topology is, it's the study of open sets. Or maybe a better way to say it, it's really the study of continuous functions. Open sets we're going to learn about today. Continuous functions we'll learn about very, very soon. The gist of it is this is all about how points in the real line, sit next to each other. And here's what I mean. We spent some time talking about the fact that R has no holes in it. If we tried to just look at rational numbers, fractions, we ran into a problem because numbers like the square root of 2, which are perfectly good numbers and we want to use them as numbers, they aren't rational. You can't write them as a fraction. So if we limited ourselves to fractions, we'd be missing lots of real numbers that we need. So we threw all those in, and now we understand that the real numbers doesn't have any holes in it. We can treat it like a continuous line that goes across. And then last go round, we learned all about absolute value and sup and inf and things like that to understand how points get close to each other, right? What it means to say that the 2 points are very close together. And so now we're going to talk about how that relates to sets. And all of this is leading, of course, to the idea of limits, which is really the central idea of calculus. We're taking a long time building up all this machinery so that we can really deeply understand what's going on when we talk about calculus ideas, the most important of which is the idea of limit, and the foundation behind all of that is understanding what it means for points to get very close to each other. And that's what's really going on behind all of this lecture. So let's get started. So first off, a very critical definition for everything we're going to be doing for the rest of this class is the idea of an epsilon neighborhood, or I often will say a ball about x of radius epsilon. The textbook will usually call it an epsilon neighborhood. But the idea is this: if we have some real number x and then some epsilon. And so throughout this, I will color my epsilons green, and you want to imagine epsilon as being sort of small, right? So epsilon's like a little small number, right? Then the neighborhood around x with radius epsilon, right, or the epsilon neighborhood of x, is this set. So, okay, I'm going to write it out in all of its full mathematical symbol glory, and we'll dissect and see what it means. So we'll always denote this with a capital N, then the point X. Then notice that's a semicolon. It's because we don't want this like an ordered pair. It's a semicolon that we'll write there, which means this happens at X, and the radius, right, is epsilon. Okay, and what is that? Right, so we have set builder notation to explain exactly what that is. Those are all the purple y's that are real numbers, so that the absolute value of x minus y is less than epsilon. And as we've learned before, what does the absolute value of x minus y really mean? It really means the distance from x to y. So a better way to read that is to say that these are all the y's, so that the distance from y to x is less than epsilon. Okay. All right, this desperately needs a picture. So here we go. Here's our x. This is the point that we're going to build a little neighborhood around, right? It's like we're putting up a subdivision or something. So we start with x, and then we have numbers around it, right? And the deal is we're looking at those purple numbers y, right, that live within epsilon of x. So I can go epsilon far away on this side, epsilon far away on the other side, right? And all of those numbers that live within epsilon of x, right, form x's neighborhood of radius epsilon, right? So what does that look like? Well, if I wanted to put the endpoints in there, that would be x minus epsilon on one side all the way over to x plus epsilon on the other side. Again, the picture you want to have in your head is that epsilon is pretty small, right? In fact, one reason why we use epsilon here is we will often be doing things later where we think of epsilon is like how far off we are, right? Like we'd like to be at x, but we can't necessarily be at x, but we want to be close. And so we'll say, well, we are within epsilon. And the reason people use epsilon is because it's sort of like epsilon is the Greek letter E, and E for error. So it's sort of like how far off we are. Okay, so it's sort of like we're trying to drive home and get to x, but at least if we can get in its neighborhood, right, then we know we're close. That's going to be the idea. Again, nothing in the definition says epsilon has to be small, right? We could have epsilon could be 15 million, and the definition makes sense. But for the things we're going to be using it for, every mathematician imagines epsilons as being for small numbers. In fact, there's a very famous mathematician who always called children little epsilons. So, okay, so this is what an epsilon neighborhood looks like. So there are times when we'll also want to talk about a deleted epsilon neighborhood of x. What is that? What do you mean deleted? What do I delete? I mean I delete the x. So the idea is sometimes, especially if we're talking about limits, I don't necessarily care what happens at x, just what happens nearby. So in with a little star, right, then the x semicolon epsilon will mean the epsilon neighborhood, but then I throw away the point x itself. So I'm just talking about the now two intervals, one on the left and one on the right of x. Okay, this needs some examples, definitely. Okay, so neighborhood around 0 of radius epsilon, well, I'm sitting at 0 and I can go epsilon in either direction. That means I can go all the way down to minus epsilon or all the way to the right to plus epsilon. All those numbers in between there, between negative epsilon and plus epsilon, that makes my neighborhood of 0. Because all those numbers between negative epsilon and plus epsilon are within epsilon of 0. Notice that this is an open interval. Notice that word open. We'll come back to that very shortly. This is an open interval with the parentheses around the, to the left of the negative epsilon and to the right of the positive epsilon there, which means that we don't include the negative epsilon or the positive epsilon. All of these neighborhoods have open intervals like this when we talk about neighborhoods. We don't include the endpoints. Okay, what about the neighborhood around 5 of radius 3? So that means I'm standing at 5 and I'm looking for all the numbers who live within 3 units of 5. So if we stop for a second and think about that, everybody got it figured out? Right? So what numbers would that be? That'd be everything from 2 all the way up to 8. Right? And if I wanted the deleted neighborhood, right, this would be n star to show that I'm deleting the 5. Right? That would be all the numbers between 2 and 8, but I throw away the point 5. And so if I wanted to keep doing this in, say, interval notation, I would write it as like the numbers from 2 to 5, then union the interval from 5 to 8. And by using, again, open intervals there, notice the parentheses, at the 5, I'm not including the 5 when I do it that way. So I go from 2 up to 5, and from 5 up to 8. I don't include the 2, the 5, or the 8 in this deleted neighborhood. Right. And again, 3 is kind of big for an epsilon. Again, usually, as I said before, we'll be doing things where epsilon's a pretty small number. So maybe a more common way you'd see this is epsilon was a really small number like 0.01. So what would be the neighborhood around negative 7, right, of radius 0.01? Right? Well, that means I would go zero point 0.01 in either direction of negative 7. That means I would go down to negative 7.01 and up to negative 6.99. And I deliberately picked a negative number to do this around, right? Because sometimes it messes with your head a little bit. When you have a negative number, negative 7.1, so 7.01 is smaller than negative 6.99, right? So that's why the order goes that way. Okay, so cool. This lets us talk about neighborhoods, and then what it means to be close to a point will be that it's inside of its neighborhood. Right? Well, next idea we need to talk about is suppose that we had a set, right, and we wanted to talk about what's inside the set. Now, those intervals we were talking about a second ago, I kept saying that you would have everything, like between 2 and 8, right? To be all the points inside that interval. So again, maybe we have a set that's not an interval, and we want to talk about all the points that are inside that set, on the inside, right? So what should that mean? Well, if a point's on the inside of a set, that means that on either side of it, right, what you see is that set, right? It's it's not, um, like an endpoint of an interval, right? That's something we'll have a name in just a second, but something that's on the inside of a set. So what that means is, right, if I wanted to draw a picture, right? So here's a number line, here's a red set S, okay? And suppose that we have a point, say a blue X right there. Okay, well, clearly, if you just look at the picture, you can tell that yes, that blue point is inside the set S, right? It's way away from the edge, right? It's not an endpoint, it's inside the set. Right? Well, what does that really mean, right? Well, in other words, if I just took that as my definition, that look, you can draw the picture and look at it and tell that it's inside, that would not help us very much at all when we started to write proofs. What we need is a definition that we can actually do something with, right? And this is where these neighborhoods really help us here, because what it means to say that that little blue dot is inside S, if you think about this and ask yourself, what should that really mean? What I mean by that is if I look to the left of x and I look to the right of x, a little bit, I can't look too far, I'll run outside my set. But if I go just a little bit to the left and a little bit to the right, then I'm still inside my set S. So in other words, I could take a little neighborhood of x and the whole neighborhood lives inside of S. Okay? Here's an analogy, right? So suppose that I live in Lubbock, right? So I'm an X and I live in Lubbock, right? What does it mean to say that I live, in the interior of Lubbock, right? Like imagine those of you who know Lubbock, the interior might be, if you live in Tech Terrace, let's say, which is very, very close to campus. For those of you who don't know anything about Lubbock, definitely in the inside part, near downtown of Lubbock. Okay? So why do I say that it's inside Lubbock? Well, that whole neighborhood around my X, right, is contained inside Lubbock. It's not like, say, for example, um, Lubbock is an odd city in that, as it's growing, once you get outside of Lubbock, there's, cotton fields and dirt until you get to Kansas. So it's, if you can sort of tell where the city stops, right? So if you were not in the interior, maybe you were right on the edge, right? Then your neighborhood might, have part inside the city and part out of the city. Here we're talking about an interior point is one where you can find a neighborhood right around you, your little neighborhood that stays completely inside the set. Now notice we're saying that there exists an epsilon because obviously, suppose in this picture I took my epsilon to be 15 billion, right? Well, then that would make a huge green neighborhood there that would run outside of S, right? So it's not that every epsilon has to do this. It's that there has to be an epsilon. So that if I look at that little epsilon neighborhood, that whole neighborhood stays inside of S. Well, okay, so another possibility besides being in the interior is being on the boundary, right? So again, this is imagine that I'm living on the very edge of town, right? Or I'm an endpoint for an interval. So what would that look like? So here's my real line, here's my red set S. So a point on the boundary, of course, would be like one of these two endpoints, right? Like that blue X right there is an endpoint of the interval. But I don't want to say endpoint because my set S wouldn't have to be always an interval, right? It might have breaks in it. It might be several intervals stuck together. What I really mean is that it's on the boundary, it's on the edge of this set because what does that mean, right? If you're out on the edge of town, that means that like one side of you is in town and the other side's not. So another way to say that is if you take a little green epsilon neighborhood around this point, then it will intersect, and part of it will be inside the red area and part of it won't. Right? So it's right on the very edge means that whenever you take a little green neighborhood around it, it will have part of it inside the set S and part of it outside. In other words, part of it will intersect S, right, and part of it won't. So for every epsilon greater than 0, then this epsilon neighborhood around X, right, well, the intersection with S won't be empty because part of it will hit S, and the intersection with the complement of S, again, that's that part outside of S, that won't be empty either, right? Because there'll be part of that neighborhood that hits S and part of the neighborhood that intersects its complement, right? So the intersection won't be empty with S and it won't be empty with the complement of S for every epsilon neighborhood. Notice this is different now because this is a for every epsilon, right? No matter how small of an epsilon neighborhood we pick around X, right? No matter how tightly we wrap our neighborhood around ourselves and we don't go very far away maybe, still, right, part of that neighborhood will lie in S and part of it will lie in the complement of S. Okay, need some examples for sure. So here's a set. This is an interval, but it's not an open interval. It's not a closed interval. It's sort of half one and half the other because we don't include the 2 in point and we do include the 8, hence the parentheses and the bracket. So this is a set that goes from 2 to 8, but it includes the 8 and not the 2. All right, well, what about the point, say, 3? Is 3 an interior point? Well, everybody got it? Yeah, of course it is, right? 3 is on the inside because this set runs from 2 to 8. So how would I prove that? Well, take a tiny little epsilon like zero point 0.1 and find a neighborhood of radius zero point 0.1 around 3. So that would go from 2.9 up to 3.1. There we go. Right? That entire set would be contained, entire neighborhood would be contained in S. So there we go. That's our proof that 3 is an interior point. I mean, besides the fact that it's pretty obvious, right? But that's how a proof of this would work. What about 5? So everybody take a second and think about 5. Pause the video if you want to for a second. Is 5 an interior point? Well, yeah, of course, right? 5 is an interior point because I could find a neighborhood around 5 of radius, say a half or a quarter or zero point 0.1 or even say 2. That would work. There's plenty of room around 5, right? So that I could find a little neighborhood around 5 that lies completely inside of S. Right? In fact, all these numbers, between 2 and 8 are interior points. Now, it doesn't count the 2 and the 8 because, of course, the 2 and the 8 are the boundary points. Right? Now, if you think about this for a second, suppose I picked a number like 7.999. Is that an interior point? Yes, definitely, right? It's an interior point. But I would need a very, very small epsilon so that my epsilon neighborhood of 7.999 stays within my set, right? I'd have to have an epsilon that was only like 0.000001, right? So that I stay that whole neighborhood that small stays within the set S. But it would work, right? There's plenty of numbers between 7.9 and 8. Or 7.99999 and 8. I just have to uh, to take an epsilon that's very, very small, right? So that I can go just a little bit closer to 8 and just a little bit further away on the other side, and that neighborhood will stay within S. Okay, so for notation purposes, we'll need to talk about the interior of a set and the boundary of a set. So to make that easier, we're instead of writing out interior, which is a long word, we'll write int S, right? That's the set of all interior points of S. And BDS, or very often in other books, you'll see that scripty D symbol, right? So that's supposed to be like a scripty D or backwards B. It also looks like the partial derivative symbol if you've seen partial derivatives. But that symbol is often also used to denote the boundary of a set. Okay? So, again, more examples. Let's say that S is this set. Now, this isn't just one interval. This is a couple of intervals stuck together, right? So we go from -4 to 2, including the 4, but not the 2. Then there's a gap, and we go from 3 to 5, again, including the 3, but not the 5. Okay, so figure out for a second what the interior and the boundary of this set S would be. If you want to pause the video for a second while you figure out what it is. Okay, everybody got it? Right? So, of course, the interior would have to be everything between -4 and 2. Again, using open intervals there, right? The -4 with a parentheses and the 2 with a parentheses, because we don't count those. Those are, of course, going to be endpoints. And then we union everything from 3 to 5. Again, not counting the 3 and the 5, because the -4, the 2, the 3, and the 5, those are all the boundary points of S. Okay, um, because of a proof we're going to be doing a little bit later, let's think about the complement of S, and let's run through the same game, right? What if we looked at R throw away S? So that's the complement of S, all the points which aren't in S, right? So what would that look like? Right? Let's write it down. So if you think about it for a second, that would be everything from -infinity up to -4. Then we skip -4 to 2. Right? Then where there was that gap in S from 2 to 3, that gets included in the complement. And then S went from 3 to 5, so the complement goes from 5 on to infinity. So this has three parts, right, in the complement. Notice that because 3 and -4 were included in S, then the complement doesn't include the -4 and the 3. But because S didn't include, at a parentheses there, at 2 and 5, that means that the complement does include 2 and 5, so they get brackets at the 2 and the 5. Okay? That's how that works. So now once we have that written down, again, it's easy to figure out what the interior of R throwaway S should be and what the boundary of R throwaway S should be. So if you want to pause the video for a second while you write it down on this piece of scratch paper. Okay, everybody got it? Okay, here we go. So the interior should be everything from -infinity up to -4. That's cool. Right? Then we union everything from 2 to 3. And again, we're using parentheses there because we don't count the 2. Then we union everything from 5 on to infinity. Right? What does happen with the -4, the 2, the 3, and the 5, of course, that's the boundary. Okay? Make sense to everybody? Cool. All right, here's another set. So this one's different than what we've had before because it's not just some intervals. This is the set which contains the number 6, so just 6 by itself. And then we're unioning that with an interval from 10 off to infinity. So the interior would be, well, everything from 10 off to infinity, of course. Um, and we don't count the 10, just like we've always done. But what about that 6? Why isn't that 6 part of the interior? Well, 6 is not part of the interior because if I take a little neighborhood around 6, let's say a neighborhood of radius 1, just to make the numbers come out nicely. So I'm standing at 6 and I go 1 unit in either direction. My neighborhood around 6 of radius 1 would go from 5 up to 7. Right? But the interval from 5 to 7 is not contained in this set S. Right? S just has one dot there at 6. There's no little neighborhood around 6 that lives inside the set S. So 6 is actually a boundary point because whenever you take a little neighborhood around 6, you'll hit something in S, namely 6, and you'll hit stuff around it which is not in S. So 6 is a boundary point, and of course so is 10. Okay, so we've used the word open and closed several times already because this is actual common algebra notation when you first learn how to write things with intervals. An interval with parentheses, right, we call open, and an interval with brackets we call closed. And the reason for that is the following definition. So here's the real definition of what it means when a set is open or closed. So if we have a set and the boundary is part of the set, then the set's closed. And if the boundary is contained in the complement, in other words, the boundary is not part of the set, then the set's open. Okay, so this is just like when we have an open interval and a closed interval, right? If you have an open interval with parentheses, right, then of course that'll be an open set because the boundary are the two endpoints and they're not in the set because of the parentheses, they're in the complement. On the other hand, if you have a closed interval, so you have brackets, so that the endpoints are included, then that means that the boundary is part of my set, and then the set's closed. So closed intervals are obviously closed. Open intervals are obviously open. Right? Now, does every set have to be either open or closed? In other words, is this like even and odd for positive integers? Where if you're not one, you're the other one. No, there are lots of sets that aren't open or closed. For example, what if you had an interval that had a bracket at one end and a parentheses at the other? right? Then sometimes people will say it's half open or half closed, or whatever. Um, that can be useful language, but we won't say that very often because that can sometimes be confusing. But what I mean by half of one, half the other, it just doesn't count as open or closed if you've got a bracket at one end and a parentheses at the other. Okay, so this is not like positive or negative or on or off or true or false. That if you're one, you have if you're not one, you have to be the other, and vice versa. You know, you can have a set which is open, you can have a set which is closed, and you can have a set which is neither. This is like functions which could be even or odd or neither. Right? If you remember about that's the way functions work. Okay, so here's a question for you to think about, right? And you'll get to think more about in the homework. Suppose that you have what we learned about maximums and soups and imps. Suppose you have an interval, right? And that interval, is my set S, and S has a max and a min. Right? What does the maximum and the minimum have to do with the boundary? Right? And what does whether or not the max and the min, right? Well, if it's set, what does whether the fact that the upper and lower bound are a max or a min, rather than just being a super and imp that aren't necessarily contained in the set, tell you about whether it's open or closed or not. Okay, I'll give you a hint, right? Suppose you have an interval and the set has a max and a min. That means it's a closed interval because the endpoints are included because you have a max or a min. But if you had a set that was an open interval, right, those would just have a sup and an inf, not a max or a min because the endpoints wouldn't be included. That would make it open because the endpoints, the boundary, would be in the complement.